Hello, my name is Muhammad Jaminur from Department of Computer Science at Western Michigan University. Today I'll talk about my work which is titled as Anomaly-Based Incident Detection in Large-Scale Smart Transportation System. In this work, we'll be focusing on incident management only, in spite having several other components in the smart transportation system. And the smart transportation system has three other approaches for monitoring, and they are crowdsourcing based monitoring, video based monitoring, and roadside sensor based monitoring. And we'll be using roadside sensor based monitoring as it has less infrastructure cost than video based monitoring approach, and it is highly reliable compared to crowdsourcing based approach. Sensor-based system architecture can be seen as this given image, where on the ground level we'll have sensors deployed per road segment that can collect the information per road segment. These collected informations cumulatively sent to a edge device which is known as roadside unit, and that roadside unit can perform some computation on this collected information to decide if that road segments contain any incident or not, and this collected information can again be sent to a cloud server for larger simulation. And the entire city area are deployed with a number of roadside units in different places for traffic incident monitoring of different parts of the area. And this architecture is already implemented in a city called Nashville from Tennessee. And also they collected ground truth incident information which is used in our work for our frameworks of validation. And we'll be detecting accidents, roadside units, and other events in this work, which requires police interventions and emergency response. And these events will be defined as traffic incidents. And also, we'll be considering traffic incidents as anomalies to apply anomaly-based approaches for incident detection. Now let's talk about the challenges we have. First, we want to set up a incident detection criteria that can help us detect the traffic incident. But due to the inherent non-recurrency and unpredictability of the smart transportation system, it is very difficult to set the detection criteria. Also, different roads with different types of pattern, different types of architecture makes it even harder to generalize the detection framework. And as humans, we are involved with these incidents or events, it is increasing the false alarm in the learned model. Also, the effective management of these thousands of road segments with different sensors are another key challenge. Our existing work studies suggest most of this work used a small region or part of the city. And even though some of the work though considered the entire city, they were validated for a smaller period of time. To claim the robustness, we need a longer period of validation. And also some of this work considered grouping of this road segment into several parts. And this was done due to detect the incidents in a distributed manner. And while doing so, they considered correlations or different geographical proximity parameter. But these parameters alone cannot bring the causal link of the clustering with the incidents. So we need to combine both of these together to bring the causal link with the incidents. And again, these proposed models has high computational cost, and our edge device has low computational capability. This high computational model cannot be deployed to detect incidents. We need lightweight framework to detect incidents efficiently. So, considering the discussion, we can generalize and categorize our contribution into two major parts. First, a spatial temporal clustering that would help us get the invariant stabilized and also bring the causal link of the incident with the clustering process. And the second contribution we have is the incident detection model per identified cluster, and that will help us detect the incident in a distributed manner. This workflow will help us visualize our entire contribution. Here we will have a graph network generator that takes the entire city road network as an input, then generates the graph network. This graph network is processed by the cluster generator and apply an approximation to generate the clusters here. After generating the clusters, we learn the detection model per cluster basis to detect the incident for that particular cluster. And before learning the detection model, another operation is performed, which is cleaning the data on which the detection model will be learned. This is because we want to reduce the bias in our learned model. Now let's talk about the invariant we'll be using for incident detection. The invariant we will be using is defined as a ratio metric between the harmonic mean and the arithmetic mean. It was first proposed in this paper IEEE TDSC 2021, where we used that invariant to detect attacks in smart metering infrastructure. And it was pretty successful in detecting attacks because it showed strict stability under benign pattern, and upon suffering with an incident or attacks, it showed strict deviation. However, for this work, we cannot adopt this invariant in a straightforward manner, because smart transportation problem itself is a separate problem with high unpredictability and uncertainty. So we have to modify the existing calculation so that it stays stable for our smart transportation incident detection. And that can be done if we can make sure our positive covariance structure is preserved under benign condition. Now let's look at these two images that demonstrate the importance of clustering. The left side image is plotted for random clustering, and the right side image is plotted for optimal clustering. In the left side image, the invariant plot shows no stability in the positive covariance structure under benign condition. At the same time, when we plot it for an actual incident, it is not showing any deviation. On the other hand, the optimal clustering is showing strict stability when for positive covariance structure under benign condition, and also showing huge deviation when there is an actual incident. And from these two results comparison, we can say to find out the incident effectively, we need to find the optimal cluster to stabilize our invariant. And from the motivation, we can achieve this clustering by transforming the road network and by applying our approximation. Now let's look at what is the transformation we are talking about. If we have a road network with 4 segments, after transformation, we can get a complete graph. And in this complete graph, we'll consider the edge weight as correlation values. And if the correlation values are less than some threshold, we will remove that edge from our consideration. This will reduce our computational complexity. Now let's look at the clustering objective. We have two clustering objectives here. First one, to cluster all the road segments that are highly correlated and closer to each other, and also minimize the number of road segments that are not highly correlated and distance to each other in a cluster. If the number of road segments that are highly correlated and are going into separate clusters, we term that as error type 1, and the opposite case is termed as error type 2. In the clustering objective formulation, we are jointly optimizing these two types of error here. And this objective optimization formulation is an NP-hard problem. We cannot solve it directly, so we rely on approximation. And this is our approximation. We start from a random node, and around that node we consider region of radius R1. And to include more road segment, we consider the distance and the correlation. Here V1, V2 both are correlated with V in it, but V1 is much more nearer. So we'll increase the region to include V1. And the radius length would be the distance between V in it to V1. In this manner, we'll keep incrementing the region until we reach the stopping criteria. And after reaching the stopping criteria, it can be defined in this slide. where we compare volume and cut. If volume is greater than cut, we stop and return the region as cluster. And volume is defined as sum of edge weights that are inside the region. It can be seen here in this picture. The black edges are the volume edges, and cut is defined as the sum of edge weights that are intersecting the region, and these red lines are the cut edges. After getting the cluster, we start learning for incident detection model. And we first design the invariant, then we clean our data so that we can remove the biases from our learning process. And then we set the detection criteria from the clean data set, and then we detect the anomalies. And this is our cleaning step. We utilize the ground truth information to locate the time range where we need cleaning. And after locating the region, we apply cumulative moving average, which is given here by this equation. This would clean the incident information from that particular located time range. For example, here in this image, region B locates the incident information. We perform a cumulative moving average from region A to region B to clean the incident information. In that way, we can reduce the incident information from our training data. This will reduce the bias in the learning. And after removing this noise, we set the threshold for the invariant, which can be calculated using this equation given in the left hand side. After setting up the threshold, we compare the invariant with this threshold, and this comparison gives us some error if there is any deviation. This error means we have a suspect for incident, and these errors are later used to calculate the stateful residual, which is which can be positive and negative. And for both of these type of residual are used to learn two type of threshold, which is one is positive and another is negative. And then this learning process is done through L1 regression. After incoming new stateful residual, it compares with the threshold, and this comparison shows us whether any time index contains incident or not. For example, in this right side image, these red dotted lines are referring to an actual incident, and after that we are seeing a deviation. That means an incident is detected. We tested our model extensively on Nashville data, but before that we used 8 months of data for training, and then 2 months of data for cross validation, and the last 2 months for testing, where we have 1 year worth of data. It contained approximately 6,000 number of intersections, approximately 19,000 number of streets, and approximately 8,000 above number of incidents. After extensive test on 2 months, we found almost 800 number of incidents, and almost 90% accuracy is provided through our detection model, and with low false positive rate. And almost 80% of these incidents were detected within 5 minutes time interval. So we can say our model is very novel in detecting incidents with low false positive rates. Also, it has novel clustering and cleaning strategy. It can be deployable in real life. And also, this research was supported by the National Science Foundation under these grants. We'd like to thank Tennessee Department of Transportation and Nashville Fire Department for help in obtaining relevant data for this research. Thank you.